This video is brought to you by the ILC. One of the most important parts of a question like this is understanding the vocabulary used. For instance, in part A, they mentioned something called critical points, so we have to give a definition of that. A critical point is just a point, x, f of x, for which f prime of x is equal to 0 or does not exist. Alright, knowing this, then our function might have some of these. We have to first take the derivative and set it equal to 0 in order to find some potential critical points. So f prime of x here is equal to the square root of 3, the negative in front, sine of x, draw that a little better. Notice that the derivative of cosine is negative sine, so I've split it up and put the negative all the way over here, which is perfectly acceptable. And then plus cosine of x. We have to set this equal to 0, so 0 is equal to this. And then somehow solve this. And there's a few ways of going about this. My favorite way is to move cosine to the other side. Have cosine of x is equal to negative square root of 3 sine of x. Then we can square both sides. We have cosine squared of x is equal to 3 sine squared of x. Change either the sine into cosine or the cosines into sines. Notice that's easier now that they're squared and we have that regular relationship that cosine squared plus sine squared is equal to 1. So in other words, cosine squared is equal to 1 minus sine squared. Then solve for x. So we're going to move the sine squared over, have 1 equals 4 sine squared of x. When we divide, we get 1/2 is equal to sine squared of x, or excuse me, 1/4, which when we take a square root of both sides, we get 1/2, and I'm going to flip the sides as well, so we have sine of x is equal to 1/2. We might even put a plus or minus here. Now, especially when we take the square of both sides, right here in this step, going from here to here, when you square both sides of an equation, it has the potential of introducing some extraneous solutions. Some solutions that just don't end up working. So it's a good idea to test it. So we're going to go back to our derivative and plug in this plus or minus 1/2 for sine. Question is, what is the corresponding cosine value? So if sine is equal to 1/2, and here we're looking at a unit circle, if sine is equal to 1/2, then what we have is either pi over 6 or negative pi over 6. Or excuse me, 5 pi over 6. If sine is equal to negative 1/2, then we have 7 pi over 6 or 11 pi over 6. Notice that all of these numbers fit in our interval from 0 to 2 pi. Alright, the corresponding cosine values of these would be right here, which is square root of 3 over 2, and right here, which is negative square root of 3 over 2. So we have 2 sine values and 2 cosine values. We're going to test every combination to figure out which ones work. So if we have negative square root of 3, this is sine of x, plus cosine of x. Let's start with this point right here, which is positive on both. Notice that all we're changing are the signs. So this is x equals pi over 6. I have negative square root of 3 times 1/2, which is our sine, plus square root of 3 over 2. You'll notice here we have negative square root of 3 over 2 plus the square root of 3 over 2, which is equal to 0. So this one works. What about the next one, which is 5 pi over 6? And you can also use your calculator to do this work for you. I'm just choosing not to here. So the sine here is positive and the cosine is negative. And this unfortunately does not equal this, it equals just the square root of 3 with a negative in front. So this one does not work. And you can keep going down the list here. You might even be able to see a pattern already. You notice that these just have to be opposites, so there are only 2 points that work for us, which is pi over 6 and 7 pi over 6. Those are our 2 critical points here. Now, those are the critical values. To find the critical points, we need to take those numbers and plug them into our original f of x in order to find the f of x here. So what is f of pi over 6? Pi over 6, we're looking at our original f here now, is the square root of 3 times cosine of x, which as we found out is the square root of 3 over 2. Then plus the sine value, which is 1/2. This is 3 over 2 plus 1 over 2, which is 4 over 2, which is equal to 2. Graph a little bit down. Then we're looking at f of 7 pi over 6. And notice that it just changes the sign of both of those. Both values are negative instead. So we have square root of 3 times negative square root of 3 over 2 plus a negative 1/2. So, makes sense then, we would have negative 2. So our 2 critical points are pi over 6 and 2, and 7 pi over 6 and negative 2. Now that we've found the critical points, our job is to find out where the function is increasing or decreasing. So this requires a number line. At least this is the way I do it. We have pi over 6 right here, and 7 pi over 6 over here. Notice that we only go from 0 to all the way to 2 pi. We don't care about numbers beyond those. So our job is to figure out what is it doing from 0 to pi over 6, from pi over 6 to 7 pi over 6, and 7 pi over 6 to 2 pi. And to figure this out, we can plug some numbers in. I'm just going to plug in 0 for this interval. In between, I'll plug in pi, let's say. And after 7 pi over 6, I'll plug in 2 pi over 4, or 3 pi over 4, excuse me. Or that's not what I want. 3 pi over 2. All right. When we plug these numbers into our values here, since I chose axis values, it makes finding f of x fairly easy. And f prime of x for that matter. Because note that we're plugging these values into f prime of x. We want to know whether it's increasing or decreasing, which means we're checking the sign of the derivative. So if we want to know sine and cosine, I'm going to label these right up here just to make sure. At 0, cosine is 1, sine is 0. At pi, we have negative 1 and 0. And at 3 pi over 2, we have 0 and negative 1. So, for the negative square root of 3, sine of x plus cosine of x, which I'll copy down here, I have for 0, the sine part turns into 0, and we just plus cosine, which is 1. So this is positive. From negative 1 to 0, or excuse me, from pi over 6 to 7 pi over 6, we're using pi as our test point, which has a cosine of negative 1 and a sine of 0, which means it's 0 plus negative 1. So negative 1, it's a negative there. And finally, we have 0 as our cosine, and our sign is -1. -1 times negative square root of 3 is positive square root of 3. So it's a positive number. Then it is increasing from 0 to pi over 6, and from 7 pi over 6 to 2 pi. Decreasing, forgive my chicken scratch here, pi over 6 all the way to 7 pi over 6. That answers that part of part A. The only other thing we have to check here is the absolute minimum and absolute maximum of the function on the interval. So I have to define those terms as well. Absolute minimum and absolute maximum have to be defined on an interval, otherwise they have the possibility of not existing. Luckily, we're given one such an interval, 0 to 2 pi. The rest, what we have to do is plot the points of all of them. We're going to find the y values of all of our critical points and all of our limits, all of the end points of our interval. So we're finding f of 0, f of pi over 6, f of 7 pi over 6, and f of pi over 2, or 2 pi, excuse me. Luckily, we've already found most of those. We know what f of pi over 6 and f of 7 pi over 6 are. They are 2 and -2. Then all we have to do is find f of 0 and f of, f of 2 pi. We're using our original f function here, so this, this up here. Well, first of all, f of 0, recall 0 has a cosine of 1 and a sine of 0, is square root of 3. And we can just fill in these pretty quickly. Pi over, and 2 pi would be identical, because this thing has the period of 2 pi. So it's also square root of 3. So our job then is to compare all of our critical values, all the y values of our critical points, and the y values of the endpoints of our interval. And the y values of our endpoints of our interval are just square root of 3, whereas the endpoints of, the y values of our critical points are 2 and -2, which are larger than square root of 3. So this value is a maximum, and this is a minimum. For part B, our job is to find inflection points and given intervals on which the function is concave upwards or concave downwards. This question is surprisingly similar, even though it uses different vocabulary. Inflection points in this problem are going to refer to places where the second derivative of our function is equal to 0. Remember, our first function said where f prime of x is equal to 0 or does not exist. And notice I never talked about the does not exist part. I only skipped that because f prime for us always exists. The domain of f prime and on this f of x is from -infinity to infinity. Alright, so f double prime of x, however, for inflection points has to equal 0. So what is f double prime? And I'll take my f prime, which is right here. F prime of x, which is equal to, or f double prime, and take the derivative of those. This is negative square root of 3 cosine of x plus, or I guess minus, sine of x. Then we have to set this equal to 0 and solve. And this is a very similar process to the previous one. We have 0 is equal to negative square root of 3 cosine of x minus sine of x. We can move the sine over and have sine of x is equal to negative square root of 3 cosine of x. When we take a square of both sides, we have sine squared of x is equal to negative square root of 3, or I guess positive 3 cosine squared of x. And we do the same thing we did, which is we turn one of the functions into 1 minus the other function. And I would recommend the one that does not have a coefficient if one exists, like in this problem. Sine squared is 1 minus cosine squared. That's equal to 3 cosine of x, which then, of course, we can turn into 1 equals 4 cosine squared of x. Divide, and we get 1/4 equals cosine squared of x, which tells us that cosine of x is equal to plus or minus 1/2. And we run into the similar problem we did last time, which is, what do we do about this plus or minus? And how do we find x knowing a cosine? We can draw our unit circle again. We have plus or minus 1/2 for the cosine this time, which gives us 4 values, which are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Knowing these values, we'll have to test the corresponding sine values as well. That is the square root of 3 over 2 and negative square root of 3 over 2. So a really similar test as well. Luckily, a lot of the work that we've done already will pay off. This time we're testing f prime. We want to find out what is negative square root of 3 cosine of x minus sine of x. What happens when we take this and we plug in x equals pi over 3? When I plug in pi over 3, let's move that down a little bit. I have negative square root of 3 cosine, which is 1/2, as we found out, and minus the square root of 3 over 2. Notice that they're both negative, so this is not going to equal the 0 that we want it to equal. Instead, it's just going to equal negative square root of 3. You can tell then that they need to be opposite signs. Since they need to be opposite signs, 2 pi over 3 and 5 pi over 3 are our inflection values. Now those are the inflection values. Remember, points have an x and a y, so we have 2 pi over 3, and 5 pi over 3. To find the y values, all we do is take our numbers and plug them into our original function. If you're really attentive, however, you may notice that this is actually just equal to this function right here. Our second derivative is just the opposite of our starting value. So if we found that the second derivative, what happens when we plug in 2 pi over 3 into our second derivative, we get 0. If our second derivative is just the opposite of our starting function, then it's also equal to 0. Because the opposite of 0 is 0. What I mean by that is this is just the original function, square root of 3 cosine of x plus sine of x, times negative 1. If I multiply this first, our original f of x times negative 1, I get f double prime of x. And thus, if this produces 0 when I plug in 2 pi over 3, the opposite of that is our original function, which is also 0. Alright, now that we found our inflection points, they also ask us for intervals on which the function is concave up or concave down. You can draw a number line right here and have our 2 inflection points and our limits listed out here. So 2 pi over 3 and 5 pi over 3 with 2 pi right here and 0 right here. And this is absolutely not proportional. We will again do some test points in between. I will set 2 pi over 3, number between 2 pi over 3 and 0 to be pi over 2. Between these two values to be pi. And between these two to be, unfortunately we don't get a good value in between them, but we can just use 2 pi because the next inflection point without those boundaries would be way past that. The same thing, we could have used 0 over here, I just chose not to. I like to avoid that when I can. When I take those numbers and plug them into the second derivative, I find that cosine of pi over 3 is 0, or pi over 2, excuse me, is 0. And sine, we can even write these down like we did before, 0, 1. This is negative 1, 0. And this is 0, or 1, 0, excuse me. So cosine sine, we have negative right here. Just running through this really quickly so we can find our answers here. Positive right here. And negative here, I believe. Right. Now a negative second derivative tells us that it's concave down. So it's concave down from 0 to 2 pi over 3. And from 5 pi over 3 2 pi. Notice again that we don't have our intervals go out to infinity, and that's just because our interval for our function is defined. The function isn't defined anywhere outside of the limits they provide. Concave up, which I use as this CC up symbol there as my abbreviation, is from 2 pi over 3 to 5 pi over 3. And that answers part B for us. Part C asks us to sketch the graph, and it has us label coordinates of the critical points, the inflection points, and the y-intercept. So we need to know one more point to sketch this graph. They want to know the y-intercept, which is just f of 0 every time. But with the corresponding x value, so it's 0, f of 0 is more accurate. The y-intercept, because the y-intercept is a point. If I plug in 0 into my original function, cosine is equal to 1, and sine is equal to 0, so it's just the square root of 3, which is actually something that we already found right here. Then let's connect the dots in order to graph. So I have 0 to 2 pi. We'll place 2 pi over here. At 0, there's the square root of 3. We know it goes all the way down to -2 and up to +2. Square root of 3 is a little bit below that, so about here maybe. It reaches the value of 2 at pi over 6 and -2 at 7 pi over 6. Pi over 6 is fairly small, so maybe here. 7 pi over 6 is going to be about here if I had to guess. The value at 2 pi we actually also know, so it might help us graph a more accurate function. It's also the square root of 3, notice. 7 pi over 6 is about halfway, so let's make that a little more accurate here. About here again. And the inflection points right here, 2 pi over 3 and 5 pi over 3, it's equal to 0. 2 pi over 3 maybe about here, 5 pi over 3 is somewhere about here. So our function looks something like this. Just a quick sketch, but as long as we've graphed it and we've included the appropriate points, we're done.